Hi, everyone, and welcome to my presentation for Connected Roundabouts. My name is Rad Lazik, and I will be your presenter today. I'm a civil engineer by trade, like most of you probably, and I've worked as a designer and engineer in transportation industry for most of my career, designing highways, interchanges, more recently, subways, and other transportation facilities. I worked on the LAX airport for the People Mover as well, and mostly dealing with software integration, customization, training, and other technical services. My specialty is putting together disparate technologies, software, exchanging models, 3D, and building information modeling. So today, we're going to talk about connected alignments. This is a feature in Civil 3D that enables us to work better and faster with intersections, and the application is also on interchanges. Then we're going to utilize some offset alignments and widening tools for a fine detail. Then we're going to use the assembly and corridor technology to complete the design. This is a fairly complex interchange and roundabout model, so we're going to require an assembly set or a little library of assemblies, also known as typical cross sections for highway design. Then we'll look at the dynamic nature of corridors and put together some fancy 3D models so that you know how to do that yourself. Obviously, the time will not permit for us to go in every detail, but I will show you the overall workflow and some of the detailed processes, and then we'll analyze some of the models that I put together for this class. So let's take a look at what's there. First of all, the overall workflow provides a lot of opportunities for integration between highway design and structures design, specifically bridges and roadways. And very popular workflow is that we start with InfraWorks that has a model builder where you can select the area of interest and collect any existing data. That is a free service, and you can utilize that online. Simply register with Autodesk with your email and password. From there, we'll collect the existing and roads and existing ground, and then send that to from that to Civil 3D to do some design. Now, once we finish with Civil 3D design, we can collect the corridors, which is basically what will be the focus of our work today, and then send those corridors to InfraWorks. InfraWorks is very good with quickly creating a conceptual bridge design and modeling. So for a typical interchange, you might end up with maybe 2, 3, 4 or more bridges. So it's very useful to be able to do that quickly in InfraWorks. Those can then be sent to Revit, and Revit can develop a structural model for fine design, to refining the design, and doing all the structural modeling and work that is done in Revit, where the design can be completed in detail. That finished design in Revit can then be sent back to Civil 3D and or InfraWorks as the requirement may be. What we will not do today, we will not work with Revit. In Revit, this is a separate class, and I encourage everyone to take some Revit classes. I'm sure there will be some that are dealing with bridges. If not, there'll be some that are dealing with exchanging data with Civil 3D at least, and InfraWorks. All right, so let's take a look at a little more detail. So we will begin first by designing some mainline alignments and profiles. Those mainline alignments are basically the intersecting roadways. Then I will build a temporary finish grade surface. This temporary finish grade surface will be used as a reference for a very quick design of the ramp surfaces profiles and curb return profiles. Then we'll do the offset, edge of travelway alignments and end profiles, because that's part of the automated system. That's the easy part. Then we do design of widening alignments for simplified exit and entrance ramps. And we do the masking for parts of the mainline widening alignments. In a very rough sketch, I'm here giving you the layout of what is the starting point. And to simplify the work, we will just use the taper for the widening, where we'll also reach the offset from the main line and arrive at the location that is about 220, 230 feet away from the actual intersection, where we will work on the two roundabout or rotary shape type of alignment. I also have the taper length about 1,500 feet, and then about 1,000 feet in the middle to accommodate the grading, side grading, and also the bridge area in the middle. Then we're going to design 4 connected alignments. Using connected alignments, we'll design 4 curb returns, or if you like, on and off ramps that are direct access to the intersecting highways. The standards that I worked from are just simply described here, and you can see that for the off ramp, the stationing will be following the direction of driving. And then, if you look at these distances, the taper itself is about 300 feet to transition from 0 to 12 feet wide lane, and then we have another 200, and then a 400. That's about 900 feet just to arrive at the point where we will depart the same formation for the road. And then we need plus additional widening or some curves to exit from the main line. So using the standard exit ramp, I will apply that and extend this 25 to 1 taper for a further 500 or 600 feet. On the entrance ramp, same situation, only the minimum requirements are even more demanding. Have a 600 feet minimum taper that translates to 70 to 1 to 50 to 1 taper. And then I have another 600 feet taper. I am not designing such horizontal curves. That's a construction level detail. So I'm just using a simple taper and also extending this for another 300 feet so that we can reach the offset from the main line so that we can do the roundabout design. Continuing with this, we will design the 2 rotaries alignments south and north of sideline and sample the finished grade surface profiles for rotaries alignments. Then we'll go and design the 4 connected alignments for curb returns. We will disconnect those so that we're able to extend and fine tune those curb returns or on and off ramps. We will then design the profiles for the 4 curb returns. This is what we will end up with. It's I call this a peanut style interchange, but it's a diamond interchange with 2 rotaries. Sometimes they're completely disconnected and completely 2 separate roundabouts. I have chosen to accept this shape where you can see what I referred to as a curb return is actually that off ramp and the opposite side on ramp. The orientation of the interchange is exactly what you see here. So I have designated the West 1 and West 2, East 1 and East 2 off ramps so that we can reference them as letters and numbers for the side, west side and east side, and maintaining the clockwise direction. All right, so I'm going to switch over to an application, Civil 3D, and jump into the just a simple layout, just to show you some of the techniques that I've employed to create these models. Other than that, we do have models completed, and we'll utilize those to explain what was done and go into more detail that way. Like I said, I began by creating a full model for this is what I refer to as a main line. So that's the freeway, and that's what I refer to as a sideline, which is the intersecting road. So for those two, obviously we designed two centerline alignments, and for mainline north and sideline east, because the mainline is in the north direction and the sideline continues to the east. From there, I also have some offset alignments created on the sideline and used for corridor modeling for the mainline and the sideline as well. I've used a couple of simple assemblies you can see on the sideline, and also it's important to say that the surface was generated from the sideline, and I have a sideline finish grade surface. This is then used to aid in design of the mainline alignment over the sideline by virtue of creating that surface model and including that in the profile. To check the clearances, I went in with 23 feet between the surface of the intersecting road and the alignment, which is the top of pavement for the main roadway. So those were the basic layout. Now, working on the main line, I'll show you some of the assemblies for that. So I'm going to go to mainline type A, and you can see that we have the median with the concrete barrier, and I also have the offset, the shoulders at 4 feet each side. Then I have a 24 feet for 2 lanes, and then the additional 8 feet for the shoulder, and then it slopes to the as a side slope. So with that in mind, I'm going to go and create offset alignments. So that's my first step. So offset alignments, as some of you may know, are created from that selected parent alignment. And I will name them using the parent alignment name, the side and the offset distance, and maybe some additional feature coding, such as edge of travelway. Actually, pardon me, this will be edge of shoulder first. So each one on the left and right, we'll go with 4 feet first, using the offsets, and simply let the software complete that step. Then I'm going to go in and do another one, another 2 actually, and those will be for, like I said, from the assemblies. Those will be at 28 on each side. Now they will be edge of travelway. And finally, the edges of shoulder, which I'm going to leave out for now and just move on to different steps. Like I said, we are going to apply widening to this edge of travelway following some of the basic standards. So I marked here to speed up the process in front of you, where we're going to start a taper and end it, do the taper at 50-1 and arrive at the location where we can join here the roundabout. In between the two, I will also have some geometry to extend about 220 feet away from the main line. So this is done by using the widening option, and I will not create a new alignment, rather edit the existing one. over here, I can start from selecting that intersection where I first sketched out schematically. The station value is the same, and finish over here. Oh, my bad. So I'm gonna go, let me do that again. And winding the orient, everything's fine except the direction. So we're gonna start from here because this goes from south to north. And I'm gonna use that intersection there. And finish that widening at the intersection point over here. Now we're gonna change the lengths of each one of the widening. So the region, total region length is 3,000 feet, but the transition parameters at entry, I'm going to have a transition length of 1,500 feet. And we're going to do a simple taper or linear transition. And I'm going to do the same for the transition out. And that's going to be also 1,500 feet. The start station will be at 500 feet, and the end station will be at the 4,000 station. So now this could be 1,500, and the region full transition region will be at 1,000 feet. So I'm just going to enter those values. This we would normally repeat on both sides of the alignment, and then we could add some additional geometry. So without spending too much more time on that, this is what you'd end up with the final product. Clearly, like I said in my slide, let's go take a look at that slide again. Oh, I didn't size them, I think. Yes, I did. So the inner circle diameter for those two roundabouts will be diameter, so it's a radius of 50, and the outer is 24 feet more, so it will accommodate 2 lanes. So that's 148 feet radius. And then for the on and off ramps joining this widening, we're going with 700 feet or 350 feet radius. So I'm going to go back to that alignments drawing, and let's take a look at quickly what we have there. So in this widening, all that's left is from basically where the, if you like, the nose of that exit ramp is. Before and after, I've utilized masking. So you can see that I've started masking from 0 to 1,400, and then again from about 3,600 to the end of the alignment. So from here, that edge of travelway offset is being masked. All right, so as you can appreciate, this is a fairly complex interchange. I'm just going to show you the number of alignments there. So the centerline alignment, do not even go to existing. That are a few hundred of them over there. So here, from the two centerline alignments, I've also designed rotary. It's actually rotary as one alignment. Let's select it. Rotary north and rotary south. They are two rotary alignments derived from those circles, and also I have offset alignment created from each one of them. As I said, offset alignments are easy to create. Here I have these curb return alignments that I used, created as connected alignments. So I simply connected between the edge of travel way on the main line and the edge of travel way on the sideline, and then I utilized the offset both sides for that alignment. Again, I utilized the masking. So I'm going to masking for parts of that alignment, or offset alignments can be created with a specific start and end station where you can stop at any time. You don't have to create offset alignment all the way through. If you look at carefully at some of the shaping of the design here, because we have the turn in to this off ramp, there's more space left for that. Where we are on the off ramp, we don't require and don't have that much. So there is no such space left. So this is the difference between the off ramp and the on ramp. So there are also a bunch of offset alignments for each one of these that you can see. And there's also curve return alignments. There are basically 4 of them. E1, which is, like I said, in the lower left corner. That's east one, and the west one is in the lower right corner. And then we are just numbering them clockwise. In the overall process, we are now where we can create the temporary surface from the roadways. Why do I need that temporary surface? Temporary surface will allow me to read elevations from the design surface on the main road and on the side road. And then I will use those to fine design the profile on my connected ramps. Temporary surface is simply created by utilizing a temporary assembly. That assembly was created to cover for the overall width, so that I have very little space left in the middle to bridge across and smooth out that transition between the two. Of course, that temporary surface can be set to have an invisible style, and you could also turn off the corridors if you don't need to see it. The main purpose is to design the finish grade. So I'm going to go to profiles and show you how did that work for profiles. I already said how we use the finish grade to design the mainline profile, but for each one of these, I utilized that temporary surface, and I also on both of the main road and the main line and the sideline. And then we just smooth out I call them curb returns, but they are off ramps and on ramps. But if you look at the overall context, they really look like curb returns. So curb returns on a at grade intersection, you can create by utilizing connected alignments. It's very easy. I might go and show you one of those. So for the connected alignments, you simply select where you want to go from the first alignment. So that would be somewhere here. And then the second alignment would be somewhere at the edge of travelway on that alignment. And this will be the location. You see how it understands the direction. And now it's asking me to accept the current location. After that, I will get this control, and I can use the design criteria. I can control the parameters. For example, in this case, I'm going to go with the radius that's 350. Also, you can design a connected profile. And when I click OK, that connected alignment will be designed in such a way. And of course, I'm just not going from the widened alignment. I'm going from the original edge of travelway. So if this is the off ramp, you can also disconnect. So if I go to alignment properties, you can work on the connection. And here it is, the update mode. You can go from dynamic to static. What that will enable you is to change any of the design. For example, you can change the overlap on both sides, or add a taper like I did to follow some general design. And basically this opens up that connected alignment to further design refinement. And that's basically what I've done before I went in there and created all the other offset alignments from those, and also connected the profile. So each profile will have its own little intrinsic design challenge and so on. I think I have here, should be profile for these. If not, we can create one. So profile for one of these rotaries, right? So what happened with rotaries, if you look carefully, the rotaries are basically running on the surface, the temporary finish grade surface. I'm going to show you what that profile is. So the temporary finish grade surface that I created from the base simple slope on the pavement and respecting the cross grades, as well as the profile on the sideline. And I'm now using that surface profile to design lanes around that rotary. There are two of them. And then the rest of it is just a simple offset alignment. Now, the offset alignment, again, is just the first pass of that design. In the next step, when we go and create corridors, the big decision was, let me just switch back to my PowerPoint. So when you move from all of your component alignments, connected, offset, widening, curb returns, rotaries, and you start thinking about creating a corridor model, this is a time for big decisions. How complex corridors can be created with multiple baselines. Basically, we have 7 controlling, actually we have 8 controlling baselines, basically, because I have 2 for the rotary, and 4 for the curb returns or on and off ramps, and then 2 for the intersecting highways. So the big decision time is what type of corridor, how will I split my corridor? I decided to create a separate corridor for each one of those alignments. First of all, because they have a lot of dependency between each other, and also because I really wanted lighter corridor models to deal with targeting and so on. So also each one of these corridors will have multiple regions, and so each region will require the maintenance of the target. So I'll explain all that once we get into the corridor model. So I ended up with main line that has a start and end region plus the middle section, I call it, ramps to ramps, and the bridge segment in the middle. The sideline has the same, instead of bridge, it has through the rotary section. And then the rotary corridor has a north and a south side. Those are 2 baselines. So this, just the rotary corridor, is a complex corridor, you can call it, because it has multiple baselines. And then I have 4 separate curb returns corridors. So I opted for 7 simpler corridors, larger number, but simpler and easier to manage. Of course, when you get into corridor modeling, then you start also working on development and managing your library of assemblies. Here are all the assemblies used in the model. And you can see that on the main line, like I said, the region when there's no connection points, that would be actually, this is further work done after my presentation class to add the retaining walls. And then you have, when there's no shoulders, even this is, if you like, going through the gore area in close proximity with the adjacent on and off ramps. And then the rest of the corridor is just a simple highway with a concrete barrier and the median. All right, so the sideline has this is real life example. So it has the median where there's just basically planters. So there's room left for planters. And then through the rotary, between the two rotaries, actually, you'll see that in the corridor model. There's just almost the same as the main line. It's important to also have on models such as this a null assembly to connect areas where there's no other assembly on any given corridor. Either that, or you're going to break that corridor into separate corridors and have nothing in between, or have some other parts of the modeling object, such as maybe grading object. Then through the rotary, you'll see in the model, I had some of the detailed requirements where we do want to have the shoulder on the inside, and then we don't want to have it past certain spot. There's that highway bridge as well. It's very simple, stock standard. Nothing, by the way, nothing custom here. No custom sub-assemblies developed or anything like that. Everything you see in this presentation is stock and comes straight from factory. I mean, if you download Civil 3D from Autodesk website for 30 days, you can use it for free as a trial. And then everything you see here can be delivered or created using that trial software. So here's at the end the corridor, and I'm going to switch over to the application. I'm going to go back to Civil 3D. It's just a slide, and sometimes it's hard to tell them apart. So this, I'm going to go and create another corridor. And here I'm going to create the RTW2. So I said RT stands for ramp and curb return, right? So in one, so this is the W1, west number 1. And this will be west number 2. So I'm going to select the alignment now, even without knowing exact alignment name. I'm just going to select that from the screen there and use the layout profile right there. That's the one that we designed. And the starting assembly is going to be from my library. I'm going to go and select it from the drawing. And here they are. I'm going to tell you something about these sub-assemblies or assemblies in a moment. So this is ramp, typical east, and the ramp is on the right. I need the one that has a ramp on the left. So I'm going to start from there. I'm going to select it right there on the assembly. And then the target surface will be existing ground. Then I'll go in there and split this corridor into multiple regions. So everything comes into one region, but I'm going to go and split that into multiple regions. So simply for this alignment, I'm going to have, I know I'm going to have first region somewhere here. Now, I don't know exactly, this will give me a clue on the opposite side, but I'm going to say, let's say somewhere here, matching that where most likely we have a beginning of a retaining wall. So that's going to be first. The second one is going to be somewhere really close to where it joins with the, let's change that to apparent intersection, where it joins with the rotary. And the rest of it will be just controlled with that edge of the rotary. So I'm going to hit enter. And I'm going to leave that as is. The fine tuning there would be to target the offset alignment. So let's take a look at how that's done. I'm going to show you something else here as part of this little exercise. So of course, we're going to change the assembly. So I like to go to modify region and control the region properties where I click inside that region, and I'm going to change the assembly where it doesn't have this is LT, no left shoulder. Also the target. So for the targets, I have the lane super elevation on the left, and I'm going to assign that to have a couple of targets there. First will be the alignment. I'm going to select that alignment on the rotary. And I'm going to select this alignment on the side and add those two as targets. And basically, I'm going to do the same thing for the elevation using the profile. Also going to use the profile on that offset alignment. And that's using that temporary surface. I'm just going to click that. So just this one to illustrate what we got. I think I have a part of the leg alignment missing there. So what happens is, I'll show you over here. So this corridor object for that on-ramp is divided into 3 parts. And if I go to corridor properties, it's not that hard to match them because I'm using that temporary surface. And I'm deriving the profile. So wherever it is on the surface, I'm staying on that surface as much as I can. And so I have no left shoulder in the first region. That's highlighted right there. And then I have direct ramp. That's a full ramp program with daylight lines and catch points there. And then no left catch point. And then I have something that even doesn't have a shoulder. Now this area here will be a separate gore area. So that will be, so I'm gonna target this edge from the main line so that the main line is gonna extend all the way from where the nose is. And then the rest of it is in the gore area. So basically repeating that about 4 times around. And then also a lot of work goes to cleaning up with where the gore area is and the nose of those on ramps and off ramps. And then as part of the modeling, Civil 3D allows us to grab all this. For example, I'm going to start from the main line and then extract corridor solids from it. And when I do, let's do that again. I had to switch off the command prompt for a good reason. And so I'm going to utilize all regions. This is only 3, but interesting part is I can add this to an existing drawing. And what happens is if I had the rest of the interchange in that existing drawing with all the solids from my corridor models, and this will just add the current one to the rest. So it's not hard to build a corridor solids model using that method. Here I am in that drawing file, a separate file where I have each one of these corridor regions as a separate solid model. Here you can see later on, I've added that bridge deck. Now, what I mentioned at the beginning, corridors can be transferred over to InfraWorks. I think we're not going to have time for that today. They have to be transferred to InfraWorks. And then instead of having this solid that doesn't really know it's a bridge, it's basically thinking it's another assembly. And then we can replace that part with the bridge model in InfraWorks and then send that bridge model over to Revit for final design and detailing. So that's how much time we had. I think I was a little ambitious. I actually have plans to show you where those two are just a simple and completely automated design for roundabouts, which you can do. And then also the very popular and very modern diverging diamond interchange, but obviously that will require a couple more hours to do. So with that, I'm going to complete and back to my PowerPoint. And thank you very much for attending my class and taking the interest in using Civil 3D for designing interchanges.